Morning,
Mohan, how are you doing? Yeah, very good
doing good.
morning. Hi Priyanka, how are you doing?
Hi, Kaustav. I'm good. I'm good.
Great, great. Okay. Let's dive in then. Okay. So in our session yesterday, we saw a bit of data understanding, like how just give me a minute. So we understood that how we can dive a bit deeper into the data and how to extract some information from the data from up data that is being given to us. Now, going ahead, we will also see how we can translate this information that we have got to insights. So that we are going to see in the upcoming sessions. However, today what we are going to do, we will touch base upon with the data preparation. Why? Because the data that we receive to work with, we cannot use that particular data to develop any models or something like that. So we have to carry out a few transformations. We have to do certain operations on those data so that we get the data in a consumable format. Okay, and that's gonna be the like agenda for the day. So we will understand a few. First, we are gonna understand this broad spectrum of data preparation. What are the things that we carry out, and then we will also we'll understand both from the theoretical aspect and also we'll see some hands-on with Excel and Python. We'll use Excel to understand what actually happens under the hood, and then we will also see how to implement the same thing on in using Python. So we start with data preparation. And when we talk about this data preparation, there are certain things that need to be discussed. So what are the different types of data preparations or the operations towards preparing data that we may carry? Okay, so there are, like we can have, we can and divide this broad spectrum into three facets. So one being imputation, second being transformation, and third is feature engineering. Now, why and when do we carry out imputation? So imputations we mainly carry out to improve the quality of the data. We carry out to improve the quality of the data. For example, let's say imputing the missing values. A lot of times we have quite a few missing values in our data, and when we have more than, like let's say uh, we cannot drop the missing values in those cases. Let's say when dropping the missing values will result in losing more than 2 to 3% of the data that we have. We cannot drop the missing values. So other what we do, we impute those missing values. Okay. So we're going to see all these things. So missing value imputation is one area because imputing the missing values will help us to improve the quality of the data. Similarly, imputing the outliers in the data as well. So these are some, like some uh, scenarios where we resort to the imputational operations. Okay. Second is the transformation. Now, transformation we carry out to reduce the overall variance or dispersion in the data. Now, when we talk about transformation, there are two kinds of transformation. One is mathematical transformation. And another is scaling of the data. Okay. Now, these terms are not exactly the terms from the book. This is how I look at the things. So if you talk about transformation in the interview, you can say that we carry out transformation to reduce the overall dispersion of the data. Now, there could be some mathematical operations like that to carry out the transformation, or we can also carry out scaling. Okay. So scaling transformation. we will talk about all these things. And then we go to the feature engineering. Now, why feature engineering is required? Because we need meaningful features for model development. Remember one thing, that when we talk about machine learning or when we talk about model development, the most important uh, part of machine learning algorithms being the feature engineering. Why? Because without the right features, we are not going to get the right kind of algorithms. Like right kind of results from the algorithms. Okay. So in feature engineering, again, there can be two aspects. One is feature selection. And another being the feature generation. Now, different feature generation can be split further, like domain-based feature generation or ML-based, and also we can go to the dimension reduction techniques and all this. But right now, I'm not, like going there. So we will limit our discussion to this part. We will limit our discussion to this part. We'll understand the transformation part because this is something that is quite important when it comes to so we are going to focus on this transformation part. So let me go to the next slide. And let's understand this data transformation. Okay. Now, why do we carry out transformation? One, so mainly we carry out transformation for several reasons. First is to reduce the overall dispersion in the data. That can be one reason. Second reason is to reduce the heterogeneity in the data. Or heterogeneity among the variables. Okay. So when we talk about the first one, to reduce the overall dispersion in the data, we mainly go for the mathematical transformation methods. For example, let's say square root transformation or logarithmic transformation. However, when we talk about when the like the focus is on to reduce the heterogeneity among the variables, we mainly go for one. We mainly go for scaling. Okay. Now in scaling, we have another two divisions. One is standardization, and another is normalization. So what happens in standardization? We convert any given distribution to standard, normal, distribution. So how do we carry out standardization? For any value, we subtract the mean of that variable, and then we divide it by the standard deviation. So I'll mention over here is x hat is mean and x double hat is the standard deviation. So in this case, what will happen? The distribution that we are gonna get after standardization will be a standard normal distribution. Why? The resultant distribution will have zero mean and unit standard deviation. We'll see that. And when we talk about normalization, we convert all the values between to a range of 0 and 1. And how do we do that? From any value, we subtract the minimum of x and we divide it by the range. Okay. That is how it goes on. So that is being the theoretical aspect more or less. Okay. Now let's understand the things in a pragmatic way. So here I have got some data with me. Okay. So for example, if you look at this data is about age. So in age, we have people ranging from 19 to 70, if you see. Okay, so it's a huge range. If you see, the standard deviation is 19.5. What does it mean? The standard deviation is 19.5 and mean is 43.2. That means this is the lower, like lower one standard deviation. And this is upper one standard deviation. So if you add one standard deviation to 43.2, you will get this. You can see I have added this. And if you subtract one standard deviation from this, you will get 23.6. That means within one standard deviation, we will have people ranging from 24 or 23 to 62. It's a huge range. We have so huge range with us that it becomes a more inconsistent kind of range to deal with. And our endeavor remains to reduce this dispersion in the data. Now, a lot of times you can go ahead and look at the box plot or something like that, and we may feel that there could be some outliers which might be doing this, but that might not be the case. Okay, you may find that there are no outliers. Still, the dispersion is quite high. Now, in that, we want to reduce this dispersion. And how we can do that? using some transformation method. Now, two popular transformation methods are the square root and the the logarithm. Okay. So in the square root, it's very simple. We go ahead and take the square root of the value that we have. And for log, we can take base 2. Now, if you look at the standard deviation, and if you look at the mean, you can see that we have reduced the overall standard deviation to a great extent. Okay. And thus the range that we are going to get now will be much more robust. Okay. So this is, like one aspect of data transformation. However, there is a one caveat to this. What is the caveat that we have when we transform the data? The meaning of the variables will also change. For example, you want to develop a model where probably it is a linear regression model. So we write like y hat equals to a plus b1 x1 plus b2 x2. Now this x1 is age. It is much more easier to interpret. However, if we are using log of age, then it will be a bit difficult to interpret. So we have to keep that in mind that if we carry out some transformation, then the same has to be, like incorporated while we interpret some kinds of output or we look at some kind of insights. Okay. So that is the first thing. Second thing is to look at the scaling of the data. Now, for this, what I've done, I have taken 3 variables: experience of a person, number of loans the person currently has, and the current income level. Okay. And let's say that, the credit bureau, they have created some kind of component, which will be 20% of experience, 20% weightage on experience, then 45% weightage on the number of loans, and 35% weightage on the income that a person has. Now, over here, we have got different values of experience, loans, and the income. Now, if you see here, what you will realize that for each of the values that we have got as a component, it is mainly dominated by the income, because the range that we have got in income is so huge that it doesn't matter how less weightage we put on it, it will always be the predominant factor in deciding the value of the component, in deciding the value of this equation that we have formed. Why so? Because income has got much larger scale as compared to experience and number of loans. That is the reason. So what we have to do, we have to reduce the heterogeneity among these variables. Now, to reduce the heterogeneity, what we have to do, we have to scale the data. We have to scale down the data. What are the benefits of scaling down? First, it reduces the heterogeneity of the data first. Second is the variables that we get after scaling, they will be free of any kind of units. So they will all be on the same page. So there are 2 methods of scaling, as we have seen, as we have discussed. One is standardization and another is normalization. So we are going to see the standardization first. So here we have the raw data. So this is the mean that we have. And this is the standard deviation that we have. So to scale this, what we have to do, we have to, let me just To scale this, from this value, we will subtract the mean. Now we will fix the cell and we are gonna divide this by the standard deviation. Okay. Next, similar, we subtract the average and we divide it by the standard deviation. And then we have the third one, income. Now, if you see the mean in this case, the mean becomes 0. Okay. And if you look at the standard deviation, it will be 1. Why the mean is 0? Because the positive values and the negative values, like they will be, because what we are doing, we are subtracting the average from the value. And then there will be some negative differences. They will negate each other. So that is why we get the mean to be 0. Now, if you look at the new component, so this, if you see now, it is not being, it is not being predominant, dominated by, rather it is now being decided by this weightage. Okay. So that is the utility of scaling. And we use scaling for multiple, occasions. What I'll do, I'll add one more sheet and I will list them out, like in which cases we use scaling. Next, normalization. Normalization is another method of scaling. Okay, I'll just give a comparison as well, like when do we go for standardization and when we go for normalization, and also which one to carry on. In case of normalization, what we have to do, from a value, we subtract the minimum value and we divide it by the range. So let me do one. Let me calculate the range here. divide it by the range. So you can see all the values are now between 0 and 1. For income is the same method. Okay. So in both the cases, what will happen? The heterogeneity among the variables will be reduced. And second, the variables will become unit free. Now we can also compare their relative importance. Okay. Now the question comes first. Where do we use scaling? So where do we use scaling? This is quite an important thing to understand. So we use scaling whenever we have to carry out dimension reduction techniques. Wherever there is a kind of, like combining multiple variables, okay, we carry out the scaling. Or let's say wherever we are using a distance based metric, for example, clustering. Okay. Why? Because in the clustering, we use the k-means clustering method where we find the Euclidean distance. So again, we need scaling. Then for algorithms like support vector machines, then k nearest neighbor. Then any gradient descent based methods, we have to scale the data. Okay. Sorry, I got disconnected, guys. So normalization or standardization. So we when there are outliers in the data, then standardization is preferred. In some cases, the model will not accept negative values as input. There, normalization should be used. However, we should carry out extensive experimentation before taking the final call. What does it mean? That we should not go by the theory. Okay, we should see which is working, because it will hardly happen that we will only do the scaling and we'll leave the data like that. What we are gonna do, we will scale the data, and then we are gonna also use something after that. So we should carry out the whole process, okay? And then we should find out that uh, which combination is working the best. Okay. So that is all about what we had to discuss. Now what we are going to do, we will see the same implementation using the Python notebook, because that's where we have to do the things.
Kaustav, what is
Yeah.
gradient descent?
We will talk about this gradient descent when we will, discuss the regression and everything. We'll
Okay.
discuss that. Yeah.
Okay.
So data preparation. So we will see transformation. Square root. Logarithmic. And then we will see scaling, standardization, and normalization. And also we'll see how we can leverage functional programming. So let's start with setting up the notebook. We'll import OS. we will give the we start get CWD. After that, we will change this working directory. And over here, we'll give the new working directory. So let me connect to the drive first. So while the previous cell gets executed, so I will import pandas as PD and also import numpy and np. Okay, now I want to show you something. So I write num equals input int input, enter a value. Okay. And over here, I first do the square root underscore num, which is np dot. And you can actually get the square root function within the numpy library. You can see we have this sqrt and we write now. Similarly, I write log underscore now np dot. So over here, you can see that there are different functions for log. I will go for log2. Okay. And I will write over here now. Now what I'll do, I will write over here print square root or dot format. Log for dot format. No. So we entered a value, let's say 144. So you can see that we have got the square root as 12.0 and the log is 7.7. That is how these two work. I just wanted to show you before we go ahead and use it on the data frame. Now I import our data. So data equals pd dot read underscore CSV. The data that we I'll take a different data frame today. Okay, let's say I take Parkinson's. Okay. Now, if I go ahead with the data dot here, just to show you the data that we have. So you can see here we have name and then we have certain variables. Okay, now one thing you can see that not all the variables are visible. Why? Because when we have a lot of variables, then a few variables get suppressed and we cannot have a look at them. So to avoid this, what we can do, we can use this pt dot set underscore option and display dot max underscore columns. Over here we give none. What does it mean? That like this, like show all the columns. So if I write instead of none, if I write 50, then what it will do, it will show us 50 columns. Okay. Now if I do the data dot head, we will get to see all the variables. Okay. Now, if in this case the first variable is a kind of character variable, we don't need that. So I just drop it. And this is how we drop it. So now once we drop it, and if I run this data dot describe, now you will find it a bit difficult because we have to scroll from left to right, okay, to have a look at the values. And that happens when we have got a lot of variables. So how to avoid this? We can also add like transpose. So what it will do, it will interchange the rows and the columns. Okay. So now for each variable, you can see standard deviation. The standard deviation, you can see that these are quite high. Okay. MDVP, these three. Rest are not that high. Okay. But the first three are quite on the higher side. So what I'm doing, I will just let me do one thing. Okay, let me do it for all the variables, no issues. So now what I'll do, I will create a copy. I will also write import copy. And I will write data underscore one, copy dot deep copy data. And for in data underscore one dot columns, data underscore one I equals np dot sqrt data underscore one I. Now, if you see data underscore one dot describe dot transpose, you can see the standard deviation being reduced to a large extent. Okay. Why? Because we have done the square root transformation. Similarly, what if we carry out data underscore two, we get another copy dot deep copy. And now what I'm doing for I in data underscore two dot columns data underscore two I equals np dot log data underscore two. And now if I do this data underscore two dot describe dot transpose, you can see that the standard deviation has been further reduced. Now there is a problem with the log method. Okay, for all, like both these variables, there is one caveat. So for example, if we have zero values or if we have negative values, then it will be very difficult or it will be impossible to get the log of the square root. Okay, so we have to also look into those things before we go ahead and before we carry out these methods. Okay. Uh, in such cases, we may have to we may have to take some other method, other steps, but otherwise we can carry out these methods. After that, we go to scaling. So transformation, square root, and now we go ahead with the scaling. So for scaling, we need some libraries. We need two libraries from sklearn dot pre-processing. We import standard scalar, min-max scalar. So standard scalar is for standardization. So I'm writing over here standardization and normalization respectively. So the first standardization. We have to instantiate the standard scalar. And then we can write like fit and transform. What does it mean? It means that it is comprised of underscore transform is comprised of two parts. One is fit, another is transform. In the fit method, it captures all the data regarding the average and the standard standard deviation for each of the variable. And then in the transform, it subtracts the mean and it divides by the standard deviation. It performs the operation. Now the problem is, if you go ahead with the head, you will not get the results. Why? Because whenever we use this fit and transform, what happens to the data is it gets converted to a NumPy array. NumPy n-dimensional array. So what we have to do, we have to convert this to data frame. And also we have to assign the columns once again. Now, if you look at dot head, you will see that the values are standardized. Okay. Similarly, for normalization, we go for the min-max scalar. And then now it will become a NumPy array. So what we are going to do over here, we will add this pt dot data frame. And also we will add the columns to it. Now, if I carry out this norm underscore data dot head, we are gonna get the normalized values. Okay. So we will stop here. In the next session, it will all be about the functional programming and the OOP. Okay, that is on Thursday. And that will create a good foundation for us to move ahead and to carry out things regarding to the data analysis. Okay. So great, guys. And meanwhile, I will share the recording along with the resources. Okay. So see you then on Thursday, same time. Till then, guys, take care. Have a nice day. Yeah. Bye-bye.
Thank you. Bye-bye.
Yeah, you're welcome. Bye.